For this problem, we examine a polynomial function. We're going to analyze the function through various parts, ultimately leading up to a graph of the function. Our polynomial function is g of x equals 2x cubed plus 5x squared minus 28x minus 15. The first thing we'd like to do is determine the maximum number of real zeros that the function may have. The maximum number of real zeros a polynomial function can have is equal to the degree of the function. We look at our function, we see this has a degree 3, so the maximum number of real zeros is n equal to 3. Next, we want to find bounds to the zeros for the function. First thing we're going to do is rewrite our function by factoring out a 2. Well, g of x is equal to 2 times x cubed plus 5 halves x squared minus 14x minus 15 halves. By factoring out the 2, we've got this reduced expression in parentheses that has a leading coefficient of 1. If we look at just this expression in parentheses, we'll have a sub 2 is equal to 5 halves, a sub 1 is equal to negative 14, and a sub 0 is equal to negative 15 halves. To find the bounds on the zeros, we need to find the maximum of 1 and the sum of the absolute value of the a's. So the absolute value of a sub 0 plus the absolute value of a sub 1 plus the absolute value of a sub 2. This will be the maximum of 1 and the sum of 15 halves plus 14 plus 5 halves. So we have the maximum of 1 and 24, which is equal to 24. We also need to find 1 plus the maximum of the absolute value of the a's. A sub 0, absolute value of a sub 1, and the absolute value of a sub 2. This will be 1 plus the maximum of 15 halves, 14, and 5 halves. So we get 1 plus 14, which is equal to 15. Now the smaller of these two numbers is 15. Well, that gives us our bound. Every 0 of g lies between negative 15 and 15. So negative 15 and 15 are the bounds on the zeros. Next, we're going to find the potential rational zeros for our function. To list the potential rational zeros, we need to look at our leading coefficient and our constant coefficient. We're going to have a sub 0, that's our constant, is equal to negative 15, and our leading coefficient, a sub 3, is equal to 2. To find the potential rational zeros, we first find the values for p, the integers p, that are factors of a sub 0. So we get p is plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Then we need integers q that are factors of our leading coefficient 2. So q will be plus or minus 1 and plus or minus 2. Now we form all possible ratios, p over q, to list our potential rational zeros. Look at all possible ratios. We'll get this ratio p over q will be plus or minus 1/2, plus or minus 1, plus or minus 3 halves, plus or minus 5 halves, plus or minus 3, plus or minus 5, plus or minus 15 halves, and finally plus or minus 15. So if our function g has a rational zero, it must be one of these 16 that we've listed here. In part D, we're asked to determine the real zeros of g, and then factor g over the reals. We're going to use the fact that if g of r equals 0, then r is a 0 of g. So we're looking for values of r that will make our function equal to 0. If we get g of r equal to 0, we can use long division to reduce our polynomial and then start again on the reduced polynomial. We made in part C a list of potential rational zeros, so we can start with that list and look for some integers that might give us g equal to 0. For instance, we can start with g of 1. If we evaluate the function g at 1, we get negative 36. Since g of 1 is not equal to 0, 1 is not a 0 of the function. If we try our next integer, the next positive integer, g of 3, g of 3 will give us the value of 0. Since g of 3 equals 0, we know that r is equal to a 0. Now we're asked to determine all the real zeros for our function g. We want to determine the real zeros of g and then factor g over the reals. For this part, we're going to use the fact that if g of x is equal to 0, then x is a 0 of our function. In part C, we found a list of potential rational zeros. We can actually use that list of potential zeros and evaluate our function at each of those to see if we get 0. We're going to do that, but we want to do it methodically, but also the easiest possible way. So we'll start with integers. We'll actually start with the positive integers. So we'll do g of 1. 1 is our first positive potential rational zero. That's an integer. We do g of 1 and evaluate the function, we'll get negative 36. Since this is not equal to 0, we know that 1 is not a 0 of g. The next positive integer potential 0 is 3. If we evaluate g of 3, we get 0. Since g of 3 equals 0, we know 3 is a 0 of the function. Therefore, x minus 3 is a factor. Since we know x minus 3 is a factor of g, we can divide g by x minus 3 and get a reduced polynomial. To do that, we need to use long division. We're going to take x minus 3 and divide into 2x cubed plus 5x squared minus 28x minus 15. If we look at 2x cubed, we need to multiply x by 2x squared to get 2x cubed. 2x squared times x is 2x cubed. 2x squared times negative 3 gives us minus 6x squared. We subtract that. 2x cubed minus 2x cubed is 0. 5x squared minus a negative 6x squared gives us 11x squared. Since the minus the negative makes it plus, we'll drop down our minus 28x. Say to get 11x squared, we need to multiply x by 11x. 11x times x is 11x squared. 11x times negative 3 is minus 33x. Again, we subtract. We do our subtraction, we'll end up with 5x. Drop down our negative 15. To get 5x, we need to multiply x by 5, so we'll have plus 5. 5 times x is 5x. 5 times negative 3 is negative 15. We subtract that, and we get a remainder of 0, which we should if x minus 3 is a factor. What that allows us to do is rewrite g of x as the product of x minus 3 and 2x squared plus 11x plus 5. We only need to worry about factoring this reduced polynomial now, 2x squared plus 11x plus 5. This is a quadratic, so we could try to factor that. We'll get x minus 3 times 2x plus 1 times x plus 5. So here we have our function g of x in factored form. To find the remaining zeros, set our last two factors equal to 0 and solve. We get 2x plus 1 equals 0. X plus 5 is equal to 0. So solving this equation, we get 2x equals negative 1, or x is negative 1/2. With this equation, we'll end up with x is equal to negative 5. Therefore, the zeros for our function are negative 5, negative 1/2, and 3. Now, if you notice, these are three rational zeros as well, and if we look back in Part C at our list of potential rational zeros, we'll see that each of these occurred in that list. Our function in completely factored form is then x minus 3 times 2x plus 1 times x plus 5. Now that we've found the zeros for our function, we're going to turn our focus to the intercepts. In Part E, we're asked to find the x and y intercepts of the graph of G. In the previous part, we found that the zeros of the function were negative 5, negative 1/2, and 3. We've also seen that x-intercepts and zeros are essentially the same thing, so our x-intercepts are negative 5, negative 1/2, and 3. To find the y-intercept, we need to evaluate g of 0. G of 0 is 2 times 0 cubed plus 5 times 0 squared minus 28 times 0 minus 15, which is just negative 15. So our x-intercepts are negative 5, negative 1/2, 3. Now our y-intercept is negative 15. If we want to write ordered pairs, the intercepts would be negative 5, 0, negative 1/2, 0, 3, 0, and 0, comma, negative 15. Next, we're going to determine whether the graph crosses or touches the x-axis at each x-intercept. If we list our intercepts, we had negative 5, negative 1/2, and 3. And we're interested in the behavior of the graph at each of those x-intercepts. Now, whether the graph crosses or touches at an x-intercept is determined by the multiplicity. We factored g of x as x minus 3 times 2x plus 1 times x plus 5. If we look at the exponent in each of these factors, we see that the exponents are all 1, which is an odd number. Each of these factors gives us one of our x-intercepts. The negative 5 comes from the factor x plus 5. The negative 1/2 comes from the factor 2x plus 1. And the 3 comes from the factor x minus 3. Since each of these factors has an odd power, the multiplicity is odd. And the behavior for an odd multiplicity is that the graph will cross at each of these x-intercepts. Had the multiplicity been even, the graph would have just touched the x-axis at the x-intercept. But each one of these had an odd multiplicity, so the graph will cross at each one. In Part G, we're looking for the power function that the graph resembles for large values of the absolute value of x. The power function is given by the term with the highest power of x. In this case, we get y is equal to 2x cubed. It's the term in our function with the highest power of x. So the graph of g will resemble the graph of 2x cubed for large values of the absolute value of x. We're just about ready to sketch the graph of our function. Before we do sketch the graph, we'd like to look at the behavior of the function near each x-intercept. In determining the behavior of the graph of our function near each x-intercept, let's first note that our x-intercepts were negative 5, negative 1/2, and 3. And that we could write our function g in factored form as x minus 3 times 2x plus 1 times x plus 5. So we look at the behavior near each of the three x-intercepts that we have. We'll start with negative 5. To find the behavior near negative 5, we're going to evaluate the function at negative 5 in each of the two factors except x plus 5. So we're going to evaluate g of x. In this first factor, we'll let x equal 5. In the second factor, let x equal negative 5. But we're not going to evaluate this third factor at negative 5 because that would give us 0. So near negative 5, g of x is approximately negative 8 times negative 9 times x plus 5. So if we put in negative 5 for x, negative 5 minus 3 is negative 8. 2 times negative 5 is negative 10, plus 1 gives us the negative 9. Again, we're not using the x plus 5 factor because we're looking at what happens near negative 5. This is equal to 72 times x plus 5. So near negative 5, the graph of g will look like a line with slope 72. Next, we'll look at the intercept negative 1/2 and do the same thing. We're going to let x equal negative 1/2 in each of the factors except for the factor that gave us this intercept. That is 2x plus 1 in this case. So g of x is going to be approximately negative 7/2 times 2x plus 1 times 9/2. If we simplify this, we'll get negative 63/2 times x minus 63/4. And so near negative 1/2, the graph of g will look like a line with slope negative 63/2. And our last intercept was 3. So we look at the behavior near 3. Following the same procedure, we're going to let x equal 3 in the two factors that did not give us this x-intercept. So g of x will be roughly x minus 3 times 7 times 8, which is equal to 56 times x minus 3. So near 3, the graph of g will look like a line with slope 56. The last part asks us to put all the information we've just obtained together so that we can get a graph of g. If we put all that information together, we get this graph for our function g. To actually obtain the graph by hand, we would need to evaluate the function at several different values for x to help determine the scale that we should use and also to help us smooth out the shape of the graph. If we look at the graph, we notice our x-intercepts. We had negative 5, we had positive 3, and we had negative 1/2. Those are our x-intercepts. And we had a y-intercept of negative 5. Notice also that we said at each of the x-intercepts that the graph would cross the x-axis there. And we see that that's exactly what's happening. At negative 5, negative 1/2, and 3, the graph crosses the x-axis. For our power function, we said that g of x would look like the graph of y equals 2x cubed for large values of the absolute value of x. We know that this is a cubic polynomial. The left end goes down, the right side goes up. And so this is in keeping with our power function 2x cubed. Some additional points would help smooth this out. We see our scale is from negative 6 to 6 along the x-axis and from negative 60 to 60 along the y-axis to give us a pretty good picture of what our function looks like.